Assalamualaikum and a very good day. Today we are going to learn how to solve for indeterminate structure using force method. This method is quite easy to understand. Hence, I am going to illustrate this method using a very simple example. And our example is a propped cantilever. So propped cantilever is a beam that is fixed at one end and propped by a roller at the other end. Okay, let's put the load as a uniformly distributed load with a value of 50 kN per meters, and let's have it length of 10 meters and call the fixed end as point A and the roller end as point B. And then let's draw the free body diagram. So at A we have reaction at A in y direction, and then we also have AX, force in x direction, and then we also have moment at A. And at point B it's a roller, so we only have reaction at A in y direction. Reaction at B in y direction. So to determine the degree of indeterminacy, the number of unknown forces or reactions, is equals to 4 RA, RB, AX and MA, and then the number of equilibrium equation is equals to 3. Okay, as we know, it's force in X, force in Y, and moment in Z direction. So as our number of unknown forces are more than the equilibrium equation, mathematically we cannot solve for this problem. Hence, this problem or structure is indeterminate to the first degree. So first degree means 4 minus 3 equals to 1. So it's indeterminate to the first degree. In this method, we are going to use principle of superposition. What we are going to do is we are going to introduce one more equation, which is called a compatibility equation. And while introducing one more equation, the number of equation will become 4 to solve for the 4 unknown forces. So this method, we are going to choose one support reaction as a redundant. In this problem, we are going to take RB as our redundant support reaction. Hence, principle of superposition, we can remove the effect of RB to the beam and make our structure as determinate. So we will remove the effect of RB. So the beam now becomes just a cantilever beam, okay, without the roller at the end, and this structure is going to be determinate and stable. So let's call this beam as our primary beam. Okay, you can actually choose any reaction as redundant. Okay, not necessarily RB. You can choose some other reaction as redundant. However, you have to make sure that your primary beam later will become determinate and stable. So for example, you can also choose MA as your redundant. So what you are going to be left is a simply supported beam, and this will be your primary structure. Okay, you can also do that, it doesn't matter. Whichever the redundant that you choose, removing the redundant must make your structure determinate and stable. Okay, either or. So let's erase this bottom part. We are not going to choose MA as our redundant. So I need to also mention that the number of redundant force will be determined by the degree of indeterminacy. In this case, because it's indeterminate to the first degree, then we need to remove one redundant to make our structure determinate. If our structure is indeterminate to the second degree, you need to remove two redundant reactions. Okay, I hope it is clear. So again, let me just rub this off. Okay, this method of superposition says that you can then add the effect of your redundant as a point load. Okay, you apply back the redundant force RB, and we are going to call this system as our redundant system. Okay, notice that superposition principle says that if you add this first beam, your primary beam, to your redundant beam, you are going to get back your actual beam here. Okay, so just a few notes. Your primary beam must have all the loads that are applied. Only the thing that is removed is only the redundant. And for your redundant system, you must remove all of your applied load. So no applied load, you are just applying the redundant force. So then we need to come out with our compatibility equation. Compatibility equation, as I mentioned before, is the other equation that you need to introduce to solve for the number of unknown. Compatibility equation in this case is compatibility of displacement. To show you the condition of displacement. So you know that for your actual beam, if you draw the deflected shape of this beam, it's going to look something like this, and the deflection as of B at point B is called delta B, which is coincidentally, because this is a roller, is going to be 0. However, for your primary beam under a uniformly distributed load, your beam is going to deflect downwards. You will have a deflection. Let's call the deflection as delta B0. So delta B0 means the first notation is the location of the point, which is point B. 0 is the system 0, which is our primary system. And then the redundant system, the deflected shape will go upwards because you are applying a load upwards. And the displacement here is called delta BB. Again, the first notation is the location of the applied load, and the second notation is the second system, which is redundant at B. Okay, so let's write down the equation, the compatibility equation. So we know that delta B, okay, the deformation displacement at B of the actual system must be equal to deformation delta B naught, the deformation due to primary beam, okay, plus the deformation due to your redundant system. Sorry, delta BB. Okay, and we know that delta B should be equal to 0. Okay, now in order to get delta BB, delta B naught, it's quite easy. You can get it from virtual method or any method that you have learned in structure analysis 1. For example, conjugate beam method, because this is just a cantilevered beam with a uniformly distributed load. However, for your redundant system here, as you can see, to get this delta BB value, you need to know what's RB, okay, the reaction at B. However, this is one of our unknown. So instead, we are going to change this system into a cantilevered beam applying a unit load and then multiplying the whole system by RB. Okay, this is basically superposition principle. This says that the deflection is just the multiplication of the force that you apply. So for this redundant case, you are still going to get the deflection upwards, and the value of this deflection is small delta BB. Okay, so this delta BB here, big delta, which is from the original problem, will then be equal to small delta BB multiplied by the reaction at B that you have applied, RB. Okay, and then if you plug it back into the original equation, so you are going to get 0 equals to delta B naught plus small delta BB multiplied by RB. And if you rearrange this equation, you will get RB as negative delta B naught divided by small delta BB. Okay, so if you know delta B naught, which you can using just virtual method, and if you know small delta BB, which again you can find out from this system using virtual method, you can then find your reaction at B. So this is in essence what force method is. Please watch the second video to see the full calculation using this method. Thank you very much.